Welcome to Topic 6, Unit 1, Finding Limits Using Tables and Graphs. You should have learned through the discovery that a limit is a y value that a graph approaches as x approaches a specific number from both sides. We use the notation the limit of f of x as x approaches c has to equal some number. Example 1. Find the limit of 5x squared as x approaches 3 using a table. So what we're going to do is we're going to input into the table x values that get closer and closer to 3 from the left and from the right. So 2.9 is very close to 3 on the left, 2.99 is closer, and 2.999 is even closer. From the right, 3.1 is closer. I'll go an order of magnitude closer at 3.01 and an order of magnitude closer again at 3.001. When I put these into my calculator, I get the following values. Now I'm most interested in what's going on right here as I'm very, very close to 3 from the left and from the right. And if you look at those y values, I appear to be approaching the number 45. So I can say that the limit as x approaches 3 of 5x squared is equal to 45. Example 2. Find the limit as x approaches 0 of sine of x over x. So again, I'm going to try to approach 0 from the left and from the right. Negative 0.1 is very close. Negative 0.01 is closer still. And finally, negative 0.001 is very close. From the right, I'll start at 0.1, 0.01, and 0.001. Now remember, when I put this into my calculator to make a table, I need to make sure that my angle is in radians. So I'll put these in my calculator and I can see that from the left and the right I am approaching 1. So the limit as x approaches 0 of sine of x over x is equal to 1. To find a limit using a graph, we have examples here. We have a case here first where f of c is not defined, but as we approach c from the left and as we approach c from the right, I'm approaching the number n. So the value of the limit is equal to n. On the second graph, you can see that f of c is defined up here, but that doesn't change the fact that as the graph approaches c from the left and approaches c from the right, we're still approaching the number n. So the limit as x approaches c of f of x is equal to n. And in our last example, it turns out that f of c does equal n, and the graph approaches c from the left and from the right and reaches n. So this is a case where f of c is equal to the value of the limit. Example 3. Find the limit as x approaches 2 of f of x if f of x is defined as this piecewise function. So if I look at the piecewise function, it is defined for when x equals 2 and for when x doesn't equal 2. So I'm going to start with where x equals 2. It says that f of x equals 1 when x is equal to 2. So that means basically that f of 2 is equal to 1. So I'm just going to draw a point at 2, 1. Now when x doesn't equal 2, I'm going to be graphing the line y equals 3x minus 2. So I will make my y-intercept 2 and I will have a slope of 3. Now keep in mind that I can't graph this line when x is equal to 2. So right here where x is equal to 2, I'm going to draw a hole and then I'm going to finish drawing my graph. So if I was to find the limit as x approaches 2, I'm going to trace the graph as x approaches 2 from the left, and I'm approaching the y value of 4, and as x approaches 2 from the right, I am approaching the y value of 4. So the value of the limit of f of x as x approaches 2 is equal to 4. Now if we only approach c from one side, we have a one-sided limit, and we use the notation that the limit as x approaches c with a negative sign of f of x is the left limit, and that's what we get when we approach c from the left. And we use the notation here, the limit as x approaches c with a plus is equal to r, the right-handed limit, because we're talking about approaching from the right. So we have an example here on the left that shows that the limit as x approaches c from the left is the same as the limit as x approaches c from the right. And when the left and the right-handed limits equal each other, then the limit exists at c. But our example here on the right shows that as we approach c from the left, our limit is equal to L, and as we approach c from the right, our limit is equal to R. And since they don't equal each other, this means that the limit as x approaches c does not exist. Example 4. Find the limit as x approaches 0 of f of x if f of x is defined as that piecewise function. So the graph changes at x is equal to 0. On the left side of 0, I'm graphing the line x. So that means that I'm going to have a point at 0, 0, and then I'm going to have a line with a slope of 1 from the left, and I'll have a closed circle at the end point x equals 0. And when x is greater than 0, I'm going to be graphing the horizontal line y equals 1. So I'll start with a hole, and I'll draw my graph pointing to the right. So if we were going to find the limit as x approaches 0 from the left of f of x, you can see that we are approaching the y value of 0. And if we were going to find the limit as x approaches 0 from the right of f of x, you can see that the y value you're approaching is equal to 1. So since the left side limit and the right side limit don't equal each other, then we say that the limit as x approaches 0 of f of x does not exist. And we say DNE for short. Example 5, use the graph to find the following. A, f of negative 2. When we look here at negative 2, we actually have a vertical asymptote. So that means that f of negative 2 is undefined, or doesn't exist. Part B, we're going to find the limit of f of x as x approaches negative 2. Well, from the left, we're approaching negative infinity, and from the right, we're approaching positive infinity. Since we're approaching positive and negative infinity, this limit does not exist. Part C, they want us to find f of 0. Well, f of 0 is up here where we have that closed circle, so f of 0 is equal to 4. D, the limit as x approaches 0 from the left. Well, as we approach 0 from the left, the y value we appear to be approaching is equal to 1/2. E, the limit as x approaches 0 from the right. Well, if I trace the graph from the right to 0, the y value I'm approaching is equal to 4. And then part F, they ask the limit as x approaches 0 of f of x. Well, since the left-hand and right-hand limits do not equal each other, the limit as x approaches 0 of f of x does not exist. Example 6. Draw a graph of a function from the functional values and limits provided. So keep in mind that as long as I meet the requirements in this problem, my graph could vary from other people's graphs. So I'm going to start first though by looking at the functional values they've given us. They've told us that f of 1 equals 3 and f of 3 equals 1. So I'm going to plot the point 1, 3 because I know that's on my graph, and the point 3, 1. The next thing I'm going to look at is the first limit that they give me, the limit as x approaches 1 from the left. Well, since f of 1 is equal to 3 already, I know that, then if the limit as x approaches 1 from the left is equal to 0, then I'm going to have to put an open circle here at x is equal to 1, 0, and then I'm just going to draw a piece of a graph that will approach this point from the left. Next, I'm going to go ahead and look at this limit right here, the limit as x approaches 3 of f of x equals negative 2. This is not a one-sided limit, so that means I have to approach 3 from both sides. But keep in mind that there is a point already defined at x is equal to 3, so again I'm going to have to put an open circle at the point 3, negative 2. And I'm going to have to make sure that I approach that value from the left and from the right. So from the right, I can just draw a piece of a graph that approaches it. But finally, let me look at the last limit. And this limit is the limit as x approaches 1 from the right of f of x has to equal 3. So I already have a point here at 1, 3, so I just have to approach it from the right. But I also have to approach this point down here from the left. So that means I can just draw a segment joining the two. And now I've drawn an example graph that meets all the requirements. That's all for now. Thanks for watching.